Here we go. Okay, so today what we're going to do is learn how to conduct a signed rank test. Last lecture, we looked at examples of the sign test. So the sign test was an alternative to the one sample t-test and the paired two sample t-test, but we only saw it in the context of a one sample t-test. The signed rank test is the same alternative. So this is actually the preferred alternative to a one sample t-test and a paired two sample t-test. And we're going to see applications of the signed rank test in both scenarios. The signed rank test, just like the sign test, is a 6-step hypothesis test where the assumptions do not require normality, or one of the assumptions is not that the population is normally distributed. So we would consider this a non-parametric test. For the most part, this test unfolds just like any other test. The null and the alternative hypotheses are going to be of the same form as they were for the sign test. So we have 3 tests about the population median. On step 3, we have the computation of a test statistic, which is the sum of the positive ranks. So we're going to look at an example of how this works momentarily. And then on step 4, we can use either a critical value or a p-value approach to determine if we have evidence for or against the null hypothesis. In this lecture set, we will actually talk about the derivation of the sampling distribution of the test statistic. So we're going to look at we are going to define the sum of the positive ranks and then show how we can use this to determine how the test statistic is going to behave. Okay, so first thing, again, our 3 hypothesis tests for the signed rank test are the same as they were for the sign test. So we have 3 tests about a population median. On step 4, we have to utilize, so on step 3, we have to compute the sum of the positive ranks. And then on step 4, we use that value to determine if we have evidence for or against the null hypothesis. Okay, so this is how we calculate the test statistic for a signed rank test. So suppose that we are testing against a population median of 11. Okay, so we have in this situation a null hypothesis that looks something like this: H0 eta equals 11, or one of the alternatives thereof. Okay, but this is the general idea. Suppose that we have a data set with 5 values in it. Okay, so we have 5 observations. To compute the test statistic, we count the number of values that are above the median, and we add their ranks together. Now, how does this work? Okay, first, take the difference between the observed value and the hypothesized median. So here we have 4. This is because 15 minus 11 is equal to 4. Then we have 1. 12 minus 11 equals 1. Then we have negative 1. 10 minus 11 equals negative 1. Okay. Then we have negative 2. 9 minus 11 equals negative 2. And then we have negative 1 again. 10 minus 11 equals negative 1. Okay, now what we have to do is rank the values in terms of how far they are from the median. The values that are closest get the smallest rank. The values that are furthest get higher ranks. Now, in this particular example, we have a tie. So you'll notice in the 3rd column, we have the absolute value of the difference. So we have taken the values that we computed in column 2, and now we have found their absolute value. So we have 4, 1, 1, 2, 1. So effectively, we're only considering the positive value now. Okay. Okay, so we have a three-way tie for rank 1. Okay, so when we have ties, we have to find a way to break the tie. Now, the way that this works is you take the sum of the ranks that could be assigned for the number of values that are tied. Okay, so step 1, add ranks for all tied values. Okay, so we have 3 values that are tied for being the closest to the median. So the 3 ranks that could be assigned here are rank 1, 2, 3. So we always have to assign ranks from 1 to the number of observations in the data set. So for these first 3 values, we would assign ranks of 1, 2, and 3. I'm just going to move this part down here. Okay, so that means that we're going to take 1 plus 2 plus 3. Okay, equals 6. And then what we would do is find average of value from 1. So that's going to be 6 over 3, which is equal to 2. Now, the value of 2 is the value that gets assigned to each of those tied ranks. So that's why in the 4th column, where we have rank of absolute DI, we have 2, 2, 2, 4, 5. Okay. So whenever we have a tie in absolute distance, we have to break the tie. The way we break the tie is by adding the ranks that could be assigned to the tie values and then taking the average of that. So we have 3 values tied for the closest to the median. So the 3 values could receive rank 1, 2, 3. When we add 1, 2, and 3 together, we get 6. When we take the average of those 3 values, we get 2. So that's why we now have a rank of 2 being assigned to those 3 numbers. Then we assign a rank of 4 to the distance 2 because that's the next value in the distance calculation. And then we assign a rank of 5 to the distance 4 because it's the furthest away. All right, now what we do is we consider which of these ranks are positive numbers. So the value 4 is a positive rank because 15 is greater than 11. The value 2 in the second row is a positive. No, they're not. Well, yeah, they are tied, but now we are assigning the proper value such that all the ranks add to 1 plus 2 plus 3 plus 4 plus 5. So the problem before was you have to, so you have these 3 values that are tied at a value, these 3 values that are tied. Because they're tied and we have to assign the rank 1, 2, 3, the problem becomes which one do we give a 1, which one do we give a 2, and which one do we give a 3? Because if we assign those individual numbers, it's going to change the value of the test statistic. So we assign the average value to all 3 of them because that way it's not over or under contributing to the test statistic. Right, so the rank 5 and the rank 2, those result from positive differences. The rank 2, 4, 2 here, those result from negative differences. So the test statistic is only the sum of the positive ranks. So the sum of 5 and 2, and that's why we have a test statistic of 7 here. Okay, so that's effectively how step 3 is going to work. And we're going to see more examples of this in a little bit when we actually look at the signed-rank test in its entirety. Any other questions, though?
I have a question.
Yes, sir.
So will the biggest rank always be like what n equals to?
Yes.
Okay.
Unless there's a tie for the 2 highest numbers, in that case, you have to break that tie. But
Okay.
yeah, you always have to assign ranks from 1 to n.
Okay. Thank you.
Yep.
I have a question too.
Yep.
So does that mean that the rank can be like a decimal?
Yeah. So if we have 2 values that are tied, the rank would be 0.5.
Okay, thank you.
Okay, so once we have the test statistic, the next thing we have to do is determine if that test statistic gives us evidence for or against the null hypothesis. So to do that, we have to have some distribution that we can utilize to determine how much evidence we have. So what I mean is, if you think back to any of the hypothesis tests we've seen so far, when we did a 2-sample t-test, the distribution that we used to find the p-value or the critical value was the student t distribution. When we did ANOVAs, the distribution that we used to find the critical value or the p-value was the f distribution. When we do a signed-rank test, what distribution do we use to find the critical value or the p-value? Well, let's just consider a couple of things here. So first, we know that if we have a set of entirely positive ranks, so if you consider, for example, something like this, where this horizontal line here is eta 0, imagine that in your data set, every single value was greater than eta 0. Okay, so this could be 1 or x1, x2, x3, x4, x little n. So this would be 1, 2, 3, 4, up to little n. So in this situation, where every single observation in the data set is greater than the hypothesized median, then the test statistic is going to be of its maximum value, okay, which is the sum of all of the ranks. So 1 plus 2 plus 3 all the way up to n. Okay, now let's consider the other situation. So suppose that, okay, we now have eta 0 here, and then we have x1, x2, x3, up to xn. Okay, in this situation, no observation is positive, which means that no rank is positive. So in this situation, W0 would be equal to 0. Okay, and again, these are observed values. Okay, so what we have just established then is that the test statistic, or the distribution of the test statistic, the smallest value it can take on is 0, and the largest value it can take on is 1 plus 2 plus 3 plus 4 plus 5 all the way up to plus n. So then we can write that the test statistic is bounded between 0 and this quantity n times n plus 1 over 2. Now this quantity here is simply 1 plus 2 plus 3 plus 4 plus n. Okay, it's just a short form for that expression. So you can sum any set of consecutive numbers from 1 up to any value by doing the number of values times the number of values plus 1 over 2. So like if you wanted to sum from 1 to 100, you would do 100 times 101 over 2, and you would get that sum. Any questions so far? Does the logic make sense? Okay. So what we have done is we've learned how to find the test statistic in sort of an illustrative way. Now what we've done is we said, okay, given how the test statistic is computed, we know that it can never be smaller than 0 and it can never be greater than the sum of all of the ranks. So it has to be between those two numbers. If the null hypothesis is true, then the median must be at the middle of this particular distribution. So the median between 0 and n times n plus 1 over 2 is just going to be the average of 0 and n times n plus 1 over 2. Okay. So this is the average of the bounds because we assume distribution is symmetric. So we're not assuming normality for the population values, but we are assuming that it is symmetric. So symmetric can happen in a lot of different ways. You don't have to be just normal. It could be a bell curve. It could be a box. It could be bimodal. It just has to be symmetric. So under the assumption of symmetry, and given the null hypothesis is true, the median and the average are the same number. So that's why we can say that the median is at the average of the two bounds. Okay, and that gives us n times n plus 1 over 4. Any questions? Okay, so if we all are in agreement, then what we have established is that for this distribution, so the distribution of the test statistic, the midpoint is at n times n plus 1 over 4. So for this particular distribution, n times n plus 1 over 4 will always be right at the middle. So any 2 points that are equidistant from the median will be equidistant from this point. Okay, how does this help us? Well, when we use a p-value or a critical value, what we do is we use or we specify cutoff points between the rejection region and the non-rejection region. That's the purpose of the critical value. So if we consider, for example, a two-tailed test, since n times n plus 1 over 4 is at the middle, that means that two critical values for a two-tailed test must be equidistant from the median. So the median of the critical values is the same median as the median of the bounds. So visually, what I mean is, if we take a graph that looks like this, okay, so here we have 0, and here we have n times n plus 1 over 2. Okay, so the min and the max. And then this plot here, this is sketch of distribution of test statistic. Okay. So we have our two bounds. In the middle, right here, we have n times n plus 1 over 4. Okay. Then a sketch of this distribution could look something like this. So we would have basically a symmetric histogram. Like that. Okay. So now if we take the two critical values, let's say we stick them right here. So here is W alpha over 2, and here is W1 minus alpha over 2. Okay, so you can see that since it's a symmetric distribution, the median is always at n times n plus 1 over 4. So the critical values are also going to be symmetric about the median, which means that we can say that the average of the critical values is that same point. So W times 1, W1 minus alpha over 2 plus W alpha over 2 divided by 2 is equal to the median. Okay. So that means that the lower bound for a signed rank test is going to be equal to n times n plus 1 over 2 minus the upper bound, where the upper bound can be found in a table of Wilcoxon signed rank values. And that table looks like this. Okay. So you can see that this table here is a function of only sample size and tail value. So we take sample size, we match it to upper tail value, just like in a student T table. And the numbers inside the table here, these are the upper tail critical values for the signed rank test. Any questions? No, and I'll show you why momentarily. Okay. But this one, it's always a function of sample size, so we'll always be directly on the table. If we get above 20, actually, if we get above 15, we don't need to use the table. So I'll show that to you in a second. Any other questions? All right, so following up on that question. So, okay, the table clearly only goes from 7 to 20. So one of the things that's pretty obvious here is that we have to have a sample size that is at least, that is 7 or more. Because if we don't have 7 or more, we can't use the table. The other thing is, what do we do when we get beyond 20? Well, actually, like with the sign test, once we get beyond a sample size of 15, we actually don't have to use the Wilcoxon distribution at all. We can use an approximation based off of a Z-score. So in the sign test case, I believe that our sample size cutoff was 10. So for the sign test, when we had 10 or more observations, we could approximate the distribution of the test statistic using the standard normal distribution. For the signed rank test, when we have a distribution of 15 or more values, we can approximate the distribution of the test statistic using a standard normal distribution as well. So therefore, we're only really going to be using the Wilcoxon test when we have sample size, or the Wilcoxon table when we have sample sizes between 7 and 14. So we're only working with this table for sample sizes of 7 to 14 inclusive. Once we get to 15 or more, we can just use the approximation based off the normal curve. Now, if you want to, you can still use the table, but you don't have to. You have the option at that point. Okay. Any questions? All right. Okay, so let's work through a full example of this now. Okay, so we have the following measurements of lengths in centimeters of randomly selected pygmy sunfish are given below. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values. At the 5% significance level, do the data provide sufficient evidence to conclude that the population median is different from 3.7? All right, so we have the following. Okay, so we have a randomly selected set of pygmy sunfish. So we can assume that the simple random sample assumption is intact here. So we're told they are randomly selected. Okay, now for symmetry, what we could do, for example, is construct a box plot to check for symmetry. Okay, so we're just looking for the values to be symmetric. We don't really have any evidence of it up the top, but if we just build like a box plot of these 10 values, then we can easily check symmetry. I don't know if there's a formal hypothesis test for symmetry. Probably wouldn't be too hard to do, but you know, a visualization will work just fine. And that's how we're going to teach it in the lab anyways. Okay, so now we're going to have H0 eta equals 3.7 versus HA eta not equal to 3.7. Okay, and then on step 2, we're going to have alpha equals 0.05. Okay, so now we have to find our test statistic. Okay, so what we're going to do here is build out our table of ranks. Okay. So we have xi, we have di, we have absolute di, we have rank, and we have sign. Okay, so we have 5.0, 3.9, 5.2, 5.5, 2.8, 6.1, 6.4, 2.6, 1.7, 4.3. Now what we're going to do is we're going to take the difference between each observed value and the hypothesized median. So 5.0 minus 3.7 equals 1.3. 3.9 minus 3.7 equals 0.2. 5.2 minus 3.7 equals 1.5. 5.5 minus 3.7 equals 1.8. 2.8 minus 3.7 equals negative 0.9. 6.1 minus 3.7 equals 2.4. 6.4 minus 3.7 equals 2.7. 2.6 minus 3.7 equals negative 1.1. 1.7 minus 3.7 equals negative 2.0. 4.3 minus 3.7 equals 1.6. 0.6. Now we're going to take the absolute values of these. 1.3, 0.2, 1.5, 1.8, 0.9, 2.4, 2.7, 1.1, 2.0, 0.6. Now we are going to rank these from smallest or from closest to furthest from the median. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, now we're going to mark down the ones that are positive. Okay, now we're going to add together the positive ranks. Okay, so that is equal to 40. Okay. Any questions? Right. Now let's just make a note about a few things for this, for the distribution of the test statistic. Okay, so for distribution of W0, the min is equal to 0. The max is equal to 10 times 10 plus 1 divided by 2, which is 55. And the median is equal to 10 times 10 plus 1 over 4, which is 27.5. So on step 4, if we take the critical value approach, we might have something that looks like this. Okay. And then this value here will be 55, and this value right here will be 27.5. Okay. All right, now it's a two-tailed test. So we're gonna have two test statistics, W alpha over 2 and W1 minus alpha over 2. Okay, so let's say that the first test statistic falls right or the first critical value falls right about here. So this is gonna be W alpha over 2. And then that means that the other critical value will be right around here, which is W1 minus alpha over 2. So now what we do is we go to our Wilcoxon table. So W alpha over 2 will be W 0.025 because we're testing at the 5% significance level. Okay. So we go to our table. We have 10 observations. We have W 0.025. That gives us 47. Now, the lower bound, this has to be found using the rule that we developed on the previous slide. Okay, so we're going to have W1 minus alpha over 2 is equal to, and then here we're going to have n times n plus 1 over 2 minus W alpha over 2. So this is going to be basically the max minus the upper bound. This value here is 8. Okay. Now, the only thing that we have left to do is mark down where our test statistic is. So we have 27.5 in the middle. We have 47 as the critical value in the upper tail. So we're probably going to be right about here. Okay. So here's W equals 40. Right, so you can see that we're outside the rejection region in this case. All right. Okay, so if we take the p-value approach, we're going to start off with a similar sketch.
Sorry, I'm trying to figure out what's the W equals 40?
That's the test statistic. Oh, W0. From right here.
Oh, okay. Sorry, thanks.
No worries. Okay, so again, we have 55 here. We have 27.5 here. Okay, so now we're looking for a p-value. So we mark down where the test statistic is. So let's say that the test statistic is about here. Okay. Okay, and then in the lower tail, we're going to have the same area, but we don't know exactly what value this is right away because it's not going to be like 40, negative 40, for example. All right. So what we would do here is we would then say, well, actually, I'm going to show you how to find the lower bound, because if we do a lower tail test, you're going to have to know how to do this anyways. So one of the things that we run into when we're finding the p-value using this approach is we can't just, well, so the areas in each tail are going to be the same size. So if we wanted to, we could get away with things like writing the p-value is equal to the probability that capital W0 is greater than 40. Two times, right? So that is true. But say that you wanted to do a lower tail test in this situation. So you only wanted the lower tail side. In order to do that, what you would have to do is find the upper tail value. Well, it's a tricky problem, actually. Okay, actually, never mind. Forget about that for now. So here's one way that we can do it. Now, just for clarity, this 2 times expression that I have written up here, maybe I'll just move this down so that we can see it a little bit more straightforward like this. Okay, so we can actually work out this value here using the same relationship we had before. So this quantity here, let's call this, I'm not sure what to call it. I guess W0 lower, maybe. So W0 lower is going to be n times n plus 1 over 2 minus W0. So that's going to be 55 minus 40, which is equal to 15. So this value here on the lower, for the lower tail p-value, that's going to be 15. So while we can just do the 2 times thing and that will work out well in this equation, it is worth just pointing out that this is the same thing as W0 less than 15 plus the probability W0 is greater than 40. Okay, so those are the same thing. Okay, so now what we would do is we would use that Wilcoxon table the same way that we do a t-table. So we would go to the Wilcoxon table, we highlight our sample size, and now we move our way through the table and we look for 40. So we can see that our test statistic is actually right here. So on this line, we are less than 41. So that means that the upper tail area is going to be greater than 0.1. So again, the way that we're using this table is exactly the same as how we use the t-table. So our test statistic is 40. 40 is smaller than 41, which means that the area to the right of 40 must be greater than 0.1. Okay, so this is size greater than 0.1, and this is a size greater than 0.1. Okay, so therefore, the p-value is going to be greater than 0.2 in this case. So then we can say that we're not going to reject H0 for the usual reason. So from this point on, everything is exactly as it was in all of our other examples. So we use the critical value in the same way we did before, and we use the p-value the same way we did before. So we're not going to reject H0 because the critical doesn't get into the rejection region, or because the p-value is larger than alpha. So then on step 6, we can say the 5% significance level, the data do not provide sufficient evidence to suggest that median length differs from 3.7. Sorry, a little cramped at the bottom there, but standard conclusion based off of our decision about the null. Okay. Does anyone have any questions?
I have a question.
Oh, yeah, sorry.
Couldn't you calculate W0 lower by just adding the rank values of the negative sign?
Yeah, it looks like that would work out too. Yep.
Okay, thanks.
Yep, no worries. Yeah, that makes good sense actually. I never thought about that before. Any other questions? Oh yeah, I guess we could do that. So at the 5% significance level, if the symmetry can be verified. Yeah, that's a good point. Thank you. So you don't have to. The only time that it's going to potentially become an issue is if you're doing a lower tail test. So it really just depends on the setup. Like it depends on where the value falls in relation to the median in that situation, which is why I wanted to show the calculation here. But like say that you're doing a two-tailed test on the assignment, you wouldn't have to show that calculation because you can just do 2 times the upper tail probability and that would be sufficient for the problem. Does that make sense?
Yeah, so like for the lower tail test, could we just do what Ben said and add the negatives, or should we just add the positives, the whole?
Well, okay, so for the lower tail test, the test statistic is always going to be the sum of the positive ranks. So in that situation, you would actually be in, what you would have to do there is find the area below the sum of the positive rank. So it would be, you would be using the, like for example, so say here our test statistic is 40, but we want to do the lower tail test. So we have found evidence that the side that the area to the right is greater than 0.1. If we do a lower tail test, we want everything below 40. So that would mean that we would then have an area that's between 0 and I guess 0.9 in that case. Do you see what I mean?
Oh yeah, I totally forgot about that. It makes sense.
Okay, so I guess that's the end of today. So I mean, as always, so on what we'll do on Monday is we'll keep working through the signed rank test, but we'll do it for paired t-tests. And then on Wednesday, we'll do the rank sum test, which is the 2 sample test alternative. So if you guys have any questions, let me know. And otherwise, have a good weekend, and I will talk to you on Monday.
On assignment 4, there's just one question, I think it's 7 or 8, where it doesn't tell us what significance to use. Is it okay if we just use 0.05?
Yeah, if it's not stated, you can always use 0.05.
Okay, thanks.